Hello students. So let's continue with our NCERT chapter 8, which is aldehyde, ketones and carboxylic acids. So today is the theory part 7 and the section which we will cover today is 8.7. This is the disclaimer. So what is the objective of today's lecture? So after attending this lecture, you will be able to understand the method of preparation of carboxylic acid. So in today's lecture, our main focus will be the preparation methods of carboxylic acids. Now for your reference, I have mapped the NCERT sections which I will be covering today. So today we will cover section 8.7, which is methods of preparation of carboxylic acids. And at last, we will summarize whatever we have learned about the preparation of carboxylic acids. So let us see the methods of preparation of carboxylic acids. So preparation of carboxylic acids, they can be done by the following method. First method is, it involves using primary alcohols and aldehydes. So this is a very common approach where primary alcohols, they are oxidized to form aldehydes, and aldehydes, they can be further oxidized to carboxylic acids. Next method, it involves the preparation from alkyl benzene. So this method involves the oxidation of alkyl side chain on benzene ring to form carboxylic acids. Another method is from nitriles and amides. So nitriles, they can be hydrolyzed to form carboxylic acids, and similarly amides can be converted to carboxylic acid through hydrolysis. Now another method is use of Grignard reagent. So Grignard reagent, they react with CO2, which is carbon dioxide, to form carboxylic acid. We can also prepare carboxylic acid from acyl halides and anhydrides. So these compounds, they can be hydrolyzed to form carboxylic acids. And finally, the carboxylic acid, they can be synthesized from esters. So this process involves hydrolysis of esters, which is a reversible reaction. Okay, so we will see that from the 6 methods we can prepare carboxylic acid. So I just gave you an overview about all these methods. Now one by one in brief we will discuss all these methods. First we will see from primary alcohols and aldehydes. So primary alcohols, they can be readily oxidized to form carboxylic acid. So it allows us to convert alcohols into carboxylic acids. Now strong oxidizing agent, they can oxidize primary alcohol directly to carboxylic acid. So this is significant. Why? Because it allows for a more efficient conversion without the need for any intermediate steps. So if you take any strong oxidizing agent from alcohol, you will oxidize directly to carboxylic acid. Now can you guess an example of a strong oxidizing agent? It can be potassium permanganate, KMnO4, or potassium dichromate, which is K2Cr2O7. On the other hand, if we are taking mild oxidizing agent, so these mild oxidizing agent will oxidize primary alcohols only to aldehyde. So if we want to stop the oxidation process at the aldehyde stage, okay, then we use mild oxidizing agent. So mild oxidizing agent includes PCC, like pyridinium chlorochromate. Now aldehydes, they can themselves further oxidized to form carboxylic acid. Okay, so you can oxidize aldehydes to carboxylic acid using both. One is a strong oxidizing agent like KMnO4, K2Cr2O7 and the Jones reagent. So they are effective in oxidizing aldehydes to carboxylic acid. Either you can also use mild oxidizing agents. So interestingly, you can also use mild oxidizing agents like Tollens reagent and Felling reagent that can oxidize aldehydes to carboxylic acids. Now, if you look at this particular reaction, okay, this will summarize the oxidation process. You're starting with a primary alcohol, which is RCH2OH, which is oxidized to an aldehyde, which is RCHO. And that aldehyde is further oxidized to a carboxylic acid, which is RCOOH. Okay, so if you use a strong oxidizing agent, alcohol will be directly oxidized to carboxylic acid. But if you're using a mild oxidizing agent, then alcohols will be first oxidized to aldehydes, and that aldehydes are further oxidized to carboxylic acids. Now, one by one, we will study all these common oxidizing agents. So, first one is KMNO4, which is which is potassium permanganate and represented as KMNO4. So this is a very strong oxidizing agent, which means it can effectively donate oxygen to other substances. Okay, so it is a strong oxidizing agent. So potassium permanganate is very versatile. Why? Because it can be used in different media. Different media, like it can be neutral, acid or alkaline. Okay, so it can be used in any of these media. So one of the key features of potassium permanganate is its ability to completely oxidize alcohols to carboxylic acid. And if you look at this particular example, you will see you have an ethanol, which is an alcohol. It is oxidized to ethanoic acid. Ethanoic acid, which is a carboxylic acid. Okay, using alkaline KMNO4, which is followed by the acidification. Okay, so you will get finally a carboxylic acid, which is CH3COOH. And if you look at the second example, you have a benzaldehyde, which is C6H5CHO. It is oxidized to benzoic acid. So from aldehyde, you are oxidizing it to a carboxylic acid. In previous example, you have alcohol, which is directly oxidized to carboxylic acid. Now you have a benzaldehyde, which is an aldehyde. It is oxidized to benzoic acid using alkaline KMNO4, which is followed by the acidification. Okay, so this shows the versatility of the potassium permanganate in oxidizing different types of compounds. Now, another oxidizing agent which we will talk about is potassium dichromate, which is represented as K2Cr2O7. Now, this is also a very strong oxidizing agent, means it can effectively transfer oxygen to other substances. But potassium dichromate is typically used in acidic media. Okay, unlike KMNO4, which can be used in any media, potassium dichromate is used in acidic medium. The acidic environment, it helps to enhance its oxidizing power, which makes the reaction more efficient. If you look at this example, you have propane 1-ol, which is an alcohol. It is oxidized using potassium dichromate. Okay, using acidic potassium dichromate, and this alcohol is oxidized to carboxylic acid, which is propanoic acid. So in carboxylic acid, if you write the name, the E of the corresponding alkane is replaced by oic, which is OIC. So this is propanoic acid. Another example you can see is an aldehyde, which is an pentanol. It is oxidized by acidic potassium permanganate to a carboxylic acid, which is pentanoic acid. It has 5 carbon atoms. So the root word will be pent. Okay, so it's pentanoic acid. Another common oxidizing agent which we will see is Jones reagent. So Jones reagent is chromium trioxide, which is CrO3 in acidic media. Acidic media is H2SO4 in acetone. Okay, so Jones reagent, it oxidizes primary alcohols to carboxylic acid. Okay, so it effectively oxidizes primary alcohols to carboxylic acids. Now it is known for its efficiency and selectivity. So it's quite efficient and it only attacks the alcohol group. specifically it attacks the alcohol group and not other parts like double bond or aromatic ring. It specifically attacks the alcohol group. If you look at this particular example, you will see that you have 1-decanol, which is an alcohol. It is using Jones reagent, which is CrO3 in acidic media, that is H2SO4 in acetone. This alcohol is oxidized to carboxylic acid. Okay, so you will see that this terminal, if you look at this particular example, this terminal CH2 group is oxidized to carboxylic acid, which is COOH. And another example you can see is 3-phenyl propane 1-ol. When you're using Jones reagent, it is further oxidized to carboxylic acid. Okay, which is 3-phenyl propanoic acid. Because if you see, we do the numbering, then 1, 2, 3. On third carbon, we have a phenyl group attached. So this is 3-phenyl propanoic acid. Now we studied first method. Now we are going to see second method. So here we are going to see that how aromatic carboxylic acids, they can be synthesized from alkyl benzenes. Okay, so this also involves oxidation. So aromatic carboxylic acids are formed through the vigorous oxidation of alkyl benzene. Okay, this means we are adding oxygen to the molecule, which is changing its structure significantly. So we will prepare the aromatic carboxylic acid by vigorous oxidation of alkyl benzenes. So to achieve this oxidation, we use strong oxidizing agents. Okay, so common example includes chromic acid and potassium permanganate. Okay, so potassium permanganate, it can be used in either acidic or alkaline conditions. So now is a very interesting aspect of this reaction. So the thing is that the entire side chain of alkyl benzene is oxidized to carboxylic acid regardless of its length. Okay, so the entire chain you will see of alkyl benzene, it will be oxidized to carboxylic group no matter what is the length of that chain. It will be completely transformed into an carboxylic group, which will simplify the structure of the molecule. Now students, there is one important thing to note, which is that only primary and secondary alkyl groups undergo oxidation. Okay, tertiary alkyl groups do not oxidize in the same way. So you need to remember that only primary and secondary alkyl groups, they undergo the oxidation process. Now if you look at this example, you have a toluene. Okay, when you treat it with KMnO4, which is a strong oxidizing agent, you will see that you will get this benzene group, a COOK groups get attached, and further acidification of this groups gives you a benzoic acid. Similarly, if you'll see, you have N-propyl benzene. N-propyl benzene, when you treat it with KMnO4, you will get this compound. So if you see that this contains 3 carbon groups, this N-propyl benzene, it contains 3 carbon atoms, but you see that whole of this entire propyl benzene is oxidized to benzoic acid. That is, this entire chain is oxidized to benzoic acid, which is COOH. Okay, so the entire chain is oxidized to carboxyl group regardless of its length. Now I have told you, like, this tertiary alkyl groups do not undergo oxidation. Okay, so it means that only the primary and secondary alkyl groups can be oxidized to form carboxylic acids. So if you look at this tertiary butyl benzene, you will see that the benzylic carbon, the carbon which is directly attached to this benzene ring, this benzylic carbon lacks the hydrogen. Okay, so that is why it does not undergo oxidation. Now the third method which we are going to see is from nitriles and amides. So we will see that how nitriles and amides, they can be transformed into carboxylic acids. So nitrile group, they react with water under acidic or basic conditions, and the hydrolysis convert your nitrile to the amide. So if you see, you have nitrile, that is R, C triple bond N, and this nitrile group is hydrolyzed to get amides. Amides is R, C double bond O, NH2. Okay, so this is often an intermediate stage if reaction conditions are mild. So if reaction conditions are mild, the reactions stop at this particular age. Okay, but if you are using stronger heating, you are doing it stronger heating or longer reaction time, then this amide breaks down into the carboxylic acid, that is this NH2 group get replaced by the OH group. So amide, they are further hydrolyzed to carboxylic acids. So once we have amide, then they can undergo further hydrolysis to form carboxylic acids. Now to facilitate this reaction, we use H plus or OH minus ions as a catalyst. So these catalysts, it helps us speed up the reaction without getting consumed in the process. Now if the reaction conditions are mild, then we can actually stop the reaction at the amide stage. So this is useful if we specifically need amides for further chemical synthesis. Okay, so if you are taking milder condition from nitrile, it will be oxidized to amide and the reaction will stop at this stage only. It won't be further hydrolyzed to give carboxylic acids. If you look at this particular example, you have benzonitrile. Okay, that is a CN group and nitrile group is attached to a benzene ring. So when you hydrolyzed it with H plus and OH minus ion, you see that you get benzoamide. Okay, benzoamide, which is a amide. So this benzoamide has a amide group. Okay, and when you further hydrolyze, you will see on further hydrolysis of this amides, you get a carboxylic acid, which is benzoic acid, and ammonia is liberated as a side product. Okay, so if the reaction conditions are mild, then you stop only at this amide stage, and if you further hydrolyze this amide, if you further hydrolyze this amide, you get a benzoic acid. Okay, so further hydrolysis of the amide gives you benzoic acid, and ammonia is released as a byproduct. Now we are going to explore the mechanism. Okay, how is this happening? So this is the mechanism of acid catalyzed amide hydrolysis. Okay, so one by one we are going to see all the steps. So first step of this mechanism involves the protonation of the oxygen atom in the carbonyl group. So this is facilitated by an acid catalyst. So if you're using an acid catalyst, then this oxygen of the carbonyl group gets protonated. So now what if it's get protonated? How is this helping this reaction? So protonation is making the carbonyl carbon more electrophilic. So if it is making it more electrophilic, it is more likely to attract nucleophiles. Okay, so first step involves the protonation of oxygen atom, which is facilitated by an acid catalyst. In next step, we have the nucleophilic addition of the water molecule. So the water molecule, which is acting as a nucleophile, it attacks the electrophilic carbon atom of the carbonyl group. So this introduces a hydroxyl group into this structure. So when this oxygen with its lone pair attack on this electrophilic carbon, you will see that it introduces the hydroxyl group. Now the next step is the when you add the water, we see the loss of the hydrogen ion or H plus ions. So this stabilizes the intermediate which is formed in this step. Okay, so you will see that oxygen gets a positive charge and oxygen never loves a positive charge. So see, we will lose this one of the hydrogen and finally you will get this intermediate. Now what will happen in next step, the amine group, that is the NH2 group, is protonated. It is being protonated to make it a better leaving group. So this amine group is protonated. So protonation is making the nitrogen atom a better leaving group. And in the further step, we will see the elimination of ammonia molecule. Now this nitrogen has a positive charge, it is NH3 plus, so this is a better leaving group. Okay, so we will see the elimination of the NH3. So this step is significant because it removes the amine group from the molecule. And what will happen in next step? Finally, we have a loss of another hydrogen ion, which results in the formation of the carboxylic acid. So when this NH3, this oxygen, the OH, the hydroxyl group in this oxygen has lone pair, so this lone pair forms a carbon double bond oxygen, and NH3 groups leave from here. And finally, there is deprotonation, that is, we lose one hydrogen to give you a corresponding carboxylic acid. Okay, so we have seen that how from amide we can convert it into carboxylic acid involving protonation, nucleophilic addition, and elimination. So I hope this mechanism is clear. Next method which we are going to see is from Grignard reagent. Okay, so we are going to prepare carboxylic acid from Grignard reagents. So Grignard reagents, they are represented as RMGX. Okay, so X over here is an halide. It can be fluorine, chlorine, bromine, or iodine. So this RMGX, it reacts with carbon dioxide. So Grignard reagent, it attacks the carbon of CO2. Okay, because the carbon of CO2 is electron poor. So this Grignard reagent attacks the carbon of CO2 and which forms a salt of carboxylic acid. So one by one we will discuss this mechanism. So after we have formed the salt, the next step is acidification. So by adding a mineral acid, we can convert the salt into a corresponding carboxylic acid. So when you add any acid like dilute HCl, it replaces MgX with hydrogen, giving carboxylic acid. Now if you look at this particular reaction, you see you have a Grignard reagent which is RMGX. When you treat it with CO2, that is carbon dioxide, and you're using dry ether. So dry ether, it prevents the destruction of the Grignard reagent by water, because Grignard reagent is highly reactive. Okay, so this dry ether, it prevents the destruction of Grignard reagent by water. So when you use Grignard reagent and CO2 in presence of dry ether, okay, you will get a salt of carboxylic acid, that is RCOO minus MgX. Okay, that is this MgX groups gets attached to this oxygen and this R groups gets attached to this carbon. Okay, and further acidification gives you a corresponding carboxylic acid. If you look at this particular example, you have phenyl magnesium bromide. Okay, when you treat it with CO2 and further you do the acidification, finally you get your product as benzoic acid. So the intermediate which is involved is a salt of carboxylic acid. Okay. Now, finally, it is important to note that this method is particularly useful for converting alkyl halides into carboxylic acid with one additional carbon atom. Okay, so this has the ability to extend the carbon chain. If you are seeing that here it is MgBr, when you use this Grignard reagent to convert alkyl halides to carboxylic acid, there is one additional carbon atom. So this has the ability to extend the carbon chain. Okay, it is important to note this thing. Now over here we will see the mechanism, that how is this reaction happening. So first step, Grignard reagents which are represented as RMGX. So this Grignard reagent, they are strong nucleophiles. So if they are strong nucleophiles, they have a high tendency to donate the electrons to other atoms or molecules. Okay. Next is the carbon and carbon dioxide, which is CO2, is electrophilic. So that means it has a partial positive charge and it is attracted to electron-rich species like nucleophiles. So Grignard reagent is acting as it has a nucleophile, and CO2 is acting as an electrophile. So in this reaction, the electrophilic carbon in CO2, it is the target for the nucleophilic attack by the Grignard reagent. So this carbon of your CO2, it is where a nucleophile attacks. Now in the next step, the nucleophilic R group from the Grignard reagent, this nucleophilic R group which has a partial negative charge, and this MgBr has a partial positive charge. So this nucleophilic R group from the Grignard reagent, it attacks the electrophilic carbon in CO2. So now this forms a new carbon-carbon bond. So if you see this R and this C, a new bond is formed. So a new carbon-carbon bond is formed. Okay. So you will see that this R gets attached to this carbon and MgBr groups get attached to this oxygen. And further acidification with mineral acid yields the corresponding carboxylic acid. Okay, so by following these set of rules or these set of steps, we will see that how from Grignard reagent we can form a carboxylic acid. So you need to remember that RMGX is acting as a nucleophile and the carbon of CO2 is acting as an electrophile. So this Grignard reagent attacks the electrophilic carbon of CO2. So this R groups get attached to the carbon, to this carbonyl group, and you will see that you will get a new carbon-carbon bond, and this OMGBr groups get attached to this O minus, and further acidification gives you a carboxylic acid. Now we are going to explore that how from acyl chlorides and anhydrides we are going to produce carboxylic acids. Okay, so we are going to see this next method, which is from acyl halides and anhydrides. So first we will see about acyl chlorides. So acyl chlorides, these compounds, they undergo hydrolysis, means they react with water to form carboxylic acids. Now, if you look at this particular equation, you have acyl acid chloride, which is RCOCl, and you will see when you react it with water or it undergoes hydrolysis, it yields a carboxylic acid, which is RCOOH. Okay, and the byproduct of this reaction is hydrochloric acid, which is HCl. So, if you look at an example, you have a propanoyl chloride, which is an acid chloride. It reacts with water and forms a propanoic acid, okay, which is a carboxylic acid, and HCl is released as a side product. So you can see that how from a acid chloride we are getting an carboxylic acid. Now we are further going to see the mechanism of hydrolysis of acid chloride, that how is this reaction happening. So first step, you will see that this H2O, okay, this oxygen which has a lone pair, it will attack this oxygen which has a lone pair, it will attack this carbonyl carbon, which is electrophilic in nature. Okay, so now you will see that this intermediate is formed, that is this H2O group gets attached to this carbon. Okay, now we will see, so the lone pair of H2O molecule, it attacks the electrophilic carbon, and which is followed by the loss of H plus. So now this oxygen has a positive charge. So we will see here the deprotonation, that this H plus is lost from here. So you get then this intermediate. And after this, in next step, you will see there is elimination of Cl minus. So this oxygen which has a negative charge, so which forms a carbon double bond oxygen, and Cl, which is a good leaving group, it leaves from here. Okay, so we have the elimination of the chloride ion, which results in the formation of a carboxylic acid. So the chloride ion is a good leaving group, that is why reaction proceeds efficiently. So finally you will see there will be elimination of Cl, which will give you a carboxylic acid. Now next step, we are going to see that acid chloride, it undergo basic hydrolysis to form carboxylate ion. So in this reaction, acid chloride react with the base to form a carboxylate ion. Once we have the carboxylate ion, the next step is acidification. So by adding an acid, we convert the carboxylate ion into a carboxylic acid. If you look at this particular reaction, you have RCOCl, which is acid chloride. When you react with the base, which is sodium hydroxide, it forms a carboxylate ion, that is RCOO minus Na plus, along with the byproducts, which is NaCl and water. And when you further add hydrochloric acid, we convert the carboxylate ion into the carboxylic acid, which is RCOOH, and NaCl is released as a side product. So starting from acid chloride, we have a carboxylic acid. So the intermediate is using basic hydrolysis, it forms a carboxylate ion. Example, if you have a benzoyl chloride, that is C6H5COCl, it reacts with hydroxide ion and water to form a corresponding benzoic acid, and HCl is released as a byproduct. Now moving on further, we will see the mechanism of this basic hydrolysis of acid chloride. Okay, so this is the mechanism. First is the attack of the hydroxide ion on the electrophilic carbonyl carbon. Okay, so the hydroxide ion, which is a strong nucleophile, it initiates the reaction by attacking the carbon atom, which is partially positive due to the electronegative oxygen. So you will see that this hydroxide minus ion, OH minus ion, it attacks the carbonyl carbon. Now, next step, we see the elimination of the chloride ion. This occurs after the hydroxide ion. It has attacked the carbonyl carbon and which has formed this tetrahedral intermediate. Now, the chloride ion, which a good leaving group, is expelled, which helps you to stabilize this intermediate. And in further step, we will see that the hydroxide ion, it abstracts a proton from the carboxylate ion. So this, which is a carboxylate ion, which is there to form a carboxylate ion. So this hydroxide ion will abstract a proton and it will give you a carboxylate ion. So this is stabilizing the negative charge that is developed on the oxygen atom. Now finally we will see there will be acidification, which will yield the carboxylic acid. So it involves you are adding a proton to a carboxylate ion, which is resulting in the formation of the carboxylic acid. Okay, so first is the attack of hydroxide ion, then there is elimination of Cl, then OH minus ion abstract H plus to give you a carboxylate ion, and then there is acidification of this carboxylate ion to give you a corresponding carboxylic acid. Now next we are going to see anhydride. Okay, we saw acid halides, now we will acyl halides, now we will see anhydrides. So anhydrides undergo hydrolysis to produce the corresponding carboxylic acid. So this reaction shows or demonstrates that how water can break down an anhydride into two acid molecules. So if you see over here, you have an anhydride. When you hydrolyze this anhydride, you get two molecules of carboxylic acid. If you look here carefully, then to this group, to this oxygen, a hydrogen gets attached, and to this C double bond O R dash, a OH gets attached. So you get a corresponding two carboxylic acids. If you look at this particular example, you have benzoic anhydride. When you hydrolyze it, you get two molecules of benzoic acid, which is a carboxylic acid. Similarly, here you have benzoic ethanoic anhydride. When you hydrolyze it, you get one molecule of benzoic acid and one molecule of ethanoic acid, because R and R dash are not same over here. Here R is C6H5 and R dash is CH3. In earlier case, R and R dash are same. Okay, so you get two molecules of benzoic acid. So if you look over here, this is C6H5, C double bond OH, and another molecule is of ethanoic acid. So one benzoic acid and one is ethanoic acid. Now if we look at the particular mechanism of this hydrolysis of anhydrides. So first step, we will see the mechanism of hydrolysis of anhydrides. So lone pairs of electrons on this water molecule, it attacks this electrophilic carbon, and after it attacks the electrophilic carbon, you will get this sort of intermediate. Okay, and next step, there is loss of hydrogen ion or H plus ions, which helps you to stabilize the intermediate which is formed. So now you will see this oxygen has a positive charge, so there is a loss of H plus H plus. So finally you get this intermediate. Next step, we see the elimination of RCOO minus group and the formation of RCOOH group. So this oxygen with this negative charge will come here, and you will see there will be C double bond O. Okay, so there is elimination of this RCOO minus group and there is formation of this RCOOH group. And finally, you will see that This RCO group minus undergoes acidification to give you a corresponding carboxylic acid. And you have two molecules of carboxylic acid. So we have converted the entire anhydride into a carboxylic acid. Okay. Now, sixth or last we are going to see is from esters. So, acid catalyzed hydrolysis of esters. Okay, so this reaction directly gives the carboxylic acid. So, acid catalyzed hydrolysis of esters gives you carboxylic acid. Now, one important thing to note here that the reaction is reversible, meaning it can go both ways under different conditions. So, the reaction is reversible in nature. This means that under certain conditions, the reaction can proceed in the opposite direction, converting carboxylic acid back into esters. So if you look at this particular example, you will see you have ethyl benzoate, which is an ester. When you do the hydrolysis, which is acid catalyzed hydrolysis, it directly gives you a carboxylic acid, which is a benzoic acid. And you get a byproduct as C2H5OH, which is ethanol. Now, we are going to next see the mechanism of this acid catalyzed hydrolysis of esters. So, in step 1, the acid catalyst play a crucial role. How? It protonates the oxygen of the carbonyl group, which is C double bond O part of an ester. So, now this makes the carbon more electrophilic, meaning it is more likely to be attacked by a nucleophile. So what is the nucleophile in this case? Water is a nucleophile in this case. So the nucleophile, which is the water molecule, that is H2O, where oxygen has its lone pair, it attacks the carbonyl carbon. Okay, so if you see over here, first it's getting protonated, and this H2O, which acts as a nucleophile, it attacks the carbonyl carbon. And you get this sort of intermediate. Now, next step is the OR, that is this OR dash group of ester gets protonated. Now we will protonate this OR dash group of ester. Why we are protonating it? So this makes this a better leaving group. Okay, so it will leave as ROH, which is an alcohol. So after this, the molecule loses a proton and resulting in the formation of carboxylic acid. So if you look carefully, we have protonated this OR group, okay, and after this you will see that this leaves as ROH, which is an alcohol. And finally, we will do the deprotonation, that is, this will lose one proton molecule to give you a corresponding carboxylic acid. So that is how from an ester we have an carboxylic acid. Now we will talk about base catalyzed hydrolysis of esters. So base catalyzed hydrolysis of esters results in the formation of carboxylates. Okay, so here you will see that the carboxylates are intermediate, which will eventually give you carboxylic acids. So once we have the carboxylate, the next step is to acidify them to obtain the corresponding carboxylic acid. Now it is also important to note here that the reaction is reversible. This means that once the carboxylic acid is, it is irreversible. Okay, that means once the carboxylic acid is formed, it does not revert back into an ester. Okay, so the nature of this reaction is irreversible in nature. If you look at this particular example, you have ethyl butanate, which is an ester. When you treat it with base catalyzed hydrolysis, it gives you a carboxylate, and further acidification of this carboxylates give you a carboxylic acid, which is a butanoic acid. Okay, so this is CH3, CH2, CH2, COOH. This is how, using a base acid hydrolysis of ester, you get carboxylate, and further acidification gives you a carboxylic acid. Now we will see the mechanism of this reaction. So first step is the attack of hydroxide ion, which attacks the electrophilic carbon of the ester. Okay, so the carbonyl carbon is partially positive, which is susceptible to nucleophilic attack. So this OH minus ion will attack this carbonyl carbon of ester group. Next, we have the elimination of OR dash group. So, this is the step where the ester linkage is broken, which is leading to the formation of an intermediate. Okay, so you will see you will be get carbon double bond oxygen, and this OR dash group will leave from here. Next, following the elimination, the hydroxide ion, it abstracts a hydrogen ion, which is H plus, to give you a carboxylate ion. So this OH minus ion abstracts this hydrogen, and this oxygen has a negative charge, and you get a carboxylate ion. And further, you will see acidification of this carboxylate ion will yield the corresponding carboxylic acid. So this completes the transformation of ester into an carboxylic acid. So this is how from ester you get a carboxylic acid. Okay, so now we will summarize all the methods which we have studied today. So first we saw the oxidation of alcohols and aldehydes. When we can oxidize a primary alcohol using strong oxidizing agent like potassium dichromate or potassium permanganate, we convert it into a carboxylic acid. Okay, and if we have a aldehyde, for the oxidation of aldehydes, we can either use it can be further oxidized to carboxylic acid using stronger or milder oxidizing agent. Next, we saw the oxidation of alkyl benzene by using chromic acid or potassium permanganate under acidic or alkaline conditions. We can oxidize alkyl benzenes to carboxylic acid. Next, we saw the method which is the hydrolysis of nitriles and amides. By treating nitriles with acid or base, which is followed by water, we can convert it into amide, and this amide can be further hydrolyzed to give you carboxylic acid. So this is a two-step process. If the reaction conditions are mild, the reaction will stop at the amide stage. Next, we saw it using Grignard reagent. By reacting a Grignard reagent with CO2, which is followed by the acidification, you get a corresponding carboxylic acid. Okay. Next, we saw the hydrolysis of acyl halides and anhydrides. So, we have acyl chloride. When it reacts with water, it forms a carboxylic acid. And in this fragment, we can see that it is a two-step hydrolysis of acid chlorides. First, the acid chloride, it reacts with hydroxide ions, which is OH minus ions, and water, and then with hydronium ions, which is H3O plus, to form a carboxylic acid. Next, we have the anhydride. Okay, when anhydride reacts with water, it gives you two molecules of carboxylic acid, which is RCOOH. Next, we saw the hydrolysis of esters. So, where we can see that this ester group, it can be converted into a carboxylic group, which is RCOOH, and we also you will see that alcohol molecule is lost in this, that is ROH, in the presence of an acid catalyzed like H3O plus, and this reaction is reversible. Okay, that it can proceed in the opposite direction also. Next, we have base catalyzed hydrolysis of esters. Here the esters react with hydroxide ion, okay, to form a carboxylic acid. And this reaction is crucial for the production of soap from fats and oils. Thank you, students, for attending this lecture. I hope the concepts which we discussed are clear. Hope you all have a nice day.